Good morning to one and all present here. A warm welcome to the webinar on Into the Heart of the Matter and Universe, organized by Department of Electronics in association with Internal Quality Assurance Cell of St. Thomas College, Autonomous Thrissur, on the occasion of National Science Day. We all know that National Science Day is celebrated on 28th of February every year to mark the discovery of Raman effect by Indian physicist Sir C.V. Raman. Before going into further details, I would like to start our session with a silent prayer. Thank you, everyone. Next, I would like to call Mr. Jinesh Paul C, Head of the Department of Electronics, to deliver the welcome address.
Good morning to all. Respected Principal Dr. Joy K.L, Vice Principal Reverend Dr. Martin Kolambrath, Resource Person Dr. Vishnudath K.N, IQAC Coordinator Dr. Father Anil George K, staff and dear students. National Science Day is celebrated in India on 28 February of each year to mark the discovery of Raman effect by Indian physicist Sir C.V. Raman. On the occasion of the National Science Day, Department of Electronics, in association with IQAC, organizing this webinar on Into the Heart of the Matter and Universe to cultivate and nourish the culture of science and its relevance in the researchers as well as in the day-to-day life. Our principal is a researcher in the field of chemical sciences and will deliver the importance of such webinars in the presidential address. I welcome our principal, Dr. Joy K.L, to this program. Our resource person, Dr. Vishnudath K.N, postdoctoral fellow, Physical Research Laboratory, Ahamedabad, is a researcher in physics, and he was our alumni. I proudly welcome you to this webinar. The Vice Principal of Jubilee Block, Reverend Dr. Martin Kolambrath, is always gave his special attention to all our day-to-day activities. I welcome Reverend Dr. Martin Kolambrath to this webinar. IQAC Coordinator, Dr. Father Anil George K, gave constant support to all the activities which empower the quality of learning. I welcome Dr. Father Anil George K to this program. I welcome all the participants to this program and hope that it will impart some knowledge and interest in the field of science. Once again, I welcome all of you to this webinar. Thank you.
Thank you, sir. Next, I would request our principal, Dr. Joy K.L, to deliver the inaugural address. Over to you, sir.
Very warm good morning to all. Resource person, Dr. Vishnudath K.N, Vice Principal, Reverend Dr. Martin Kolambrath, IQC Coordinator, Reverend Dr. Anil George Kongoth, Head of the Department, Mr. Jinesh Paul, Coordinator, Ms. Rithusree K.J, faculty members, and dear students. It adds to the pleasure of our college as we learned that the Department of Electronics organizes a webinar on Into the Heart of Matter and Universe on the occasion of National Science Day 2021. We know the objectives of celebrating National Science Day is to spread a message about the importance of science used in the daily life of the people. It is also celebrated to discuss all the issues and implement new technologies for the development in the field of science. In this context, today's webinar is very significant and it is useful for the participants. We know matter is conserved and stores energy. Matter is life, and it is true to say that matter makes up reality. Let me express sincere gratitude to Dr. Vishnudath K.N, a postdoctoral fellow, Physical Research Lab, Navarangpura, Ahamedabad, for his guidance for our intellectual exercise. I hope this webinar will be quite helpful to our students to know more about matter and universe. Let me make use of this opportunity to congratulate and thank Mr. Jinesh Paul, the head of the Department of Electronics, Ms. Rithusree K.J, the coordinator of this webinar, and all the colleagues in the department on behalf of the management and administration of the college. Wishing one and all the best, let me declare with your permission the webinar on Into the Heart of Matter and Universe open. Thank you very much.
Thank you, sir. Next, I would request our Vice Principal, Reverend Dr. Martin Kolambrath, for the felicitation.
Respected Principal Dr. K.L. Joy, Professor Jinesh Paul C, and Professor Rithu, Dr. Vishnudath, our alumni, former alumni, and their students and participants. From time immemorial, it has been a great thought of the philosophers. What is the heart of matter and universe? And different philosophers have always given different answers. Some said it is water, some said it is fire, some said it is air. That is the heart of any matter. And now we are again discussing the perennial theme, and I'm glad that it is one of the alumni, Dr. Vishnudath, handling this subject, very interesting subject, which is to be thought of this when commemorating the Science Day. So wishing you all the best, and congratulating the department for organizing such a webinar. Let me conclude. Thank you. I'm interested in the matter to know what's there to the matter. Thank you so much. All the best. Thank you.
Thank you, Father. Next, I would request our IQAC coordinator, Dr. Father Anil George K, for felicitation.
Good morning, respected Dr. Joy K. Principal, Father Martin, Vice Principal, the resource person of the day, Jinesh Paul and faculty members and my dear participants of this webinar. I'm very happy that this is the time, this is an occasion when we incorporate and focus on scientific temper and scientific development among the students. This is the time we go after so many misconceptions and prejudices and blind faiths, and it's very important that we have scientific temper when we approach different realities of life. And it is good that the department is organizing such an event, and the department of electronics vibrant. We have very good youngsters in the department, the faculty members. I'm very happy to congratulate the department for having organized this particular event, and my IQAC is very happy to collaborate with this event as well. And I wish all the best for the successful completion of this event, and I hope that the event produces the expected results in the days to come.
Thank you, Father. Now we are moving on to the technical session. I am privileged to have such an eminent personality and our alumni, Dr. Vishnudath K.N, Postdoctoral Fellow, Theoretical Physical Division, Physical Research Laboratory, Ahamedabad, as our resource person. I request to handle the technical session. Over to you, sir.
Hi, good morning, everyone. Okay, first of all, I would like to thank the organizers for giving me this opportunity to give this talk here. And it's such a pleasure to give this talk in front of the students and teachers of my own college. And yeah, having said that, let me directly go to my talk. So yeah, as it was already mentioned, the title of my talk is Into the Heart of Matter and Universe. And I work on theoretical particle physics. And in particle physics, what we study is like what the universe is made of and how the elementary particles interact among themselves. So I thought on this day it would be nice to give you a brief overview of the research that is being done in this direction. And yeah, the theme for this is future of science, technology, and innovation, and its impact on education. As I mentioned, I will talk about things that we made in our understanding of the universe during the future prospects. Okay. So like science and technology like have hand in hand to develop our understanding of the basic physics, the understanding of our universe. And okay, so I would like to start with some of the major milestones in the past. So most of you must have heard of these headlines. Like, so the first is the discovery, simple discovery of the Higgs boson at the Large Hadron Collider, and next year, Professor Higgs and Professor Frank Glad were awarded the prize in physics, and then 2015 Nobel Prize for the discovery of neutrino oscillation, which showed that was massive. And then in 2016, we also observed waves in the LIGO experiment. It was proposed by a century ago, and this was awarded with the Nobel Prize in Physics. So in this talk, I'll focus on the first two aspects, like especially me being a particle physicist, and also due to the time constraints, I would focus on the particle physics aspects. So why particle physics? Why should we study particle physics at all? So in particle physics, the most fundamental questions that we ask elementary constituent forces that control behavior. First of all, what is the word that has been asked by science since very ancient times? So earlier it was mentioned, like that the world was made of these four elements: air, fire, water. Everything is made of. It's a very simple, but then it has one drawback. It is wrong.
Sorry for the interruption.
Hi, I hope I'm audible.
Okay, sir. You can continue.
Yeah, sorry, there was some technical glitches. I don't know what happened. So yeah.
Yeah.
Okay, so yeah, we have studied about the atomic models, like even in high school. So first there was this Dalton's model, like according to which he considered atoms are these small billiard balls, and that cannot be further divided. But then J.J. Thomson came up with the plum pudding model, in which he considered atom as a positive spherical fluid in which the electrons were distributed like the plums in the pudding. And then Rutherford said that it was strong, and from with the inferences from his scattering experiments, he came up with the planetary model, where he compared the motion of the electrons around the nucleus to the motion of the planets around the sun in our solar system. And then Bohr came up with his model because there were certain issues that Rutherford's model couldn't explain, such as why atoms emit radiations only in certain frequencies. So then Bohr came up with the orbit model. And then finally, now we have the quantum mechanical model of the atom, I mean, that was improved upon by like various scientists, including Louis de Broglie and Erwin Schrödinger. So now, like we consider, like we cannot exactly determine the position of the electron in the orbits of an atom. Instead, all we can talk about the probabilities of finding an electron in the particular orbit. So yeah, moving on from atoms. Now we know anyway. Like there is in an atom there is a nucleus, and the electrons are revolving around the nucleus in the atom. But then the nucleus again consists of neutrons and protons, which we know. But then are these neutrons and protons really fundamental? So it turned out that they are not really fundamental. Again, as shown by some various scattering experiments, that the nucleus also that the neutrons and protons also have an internal structure. In fact, they are made of some extremely tiny particles which are called as quarks. So here we can see like the size of these quarks with respect to the size of the atom. The size of an atom is of the order of 10 to the power of minus 8 centimeter, whereas the size of a nucleus is of the order of 10 to the power of minus 12 centimeter. And the proton is one order of magnitude smaller than neutrons, and finally we have quarks, which are like much tinier. Now, to probe such small, extremely small distance scale, we need extremely high energy. So that means we need actually high momentum, and that is why particle physics is known as high energy physics. So this we can also understand from the uncertainty principle. We know that the product of the uncertainty in position and the uncertainty in momentum is greater than h. And if we want to probe into smaller and smaller distances, we need larger and larger momentum. Now, like coming to the frame of particle physics, like I would like to briefly mention how we study high energy physics. Sorry. Okay. Now, in the in our day-to-day life, for example, suppose we want to describe the motion of a car or the motion of a train, we use classical mechanics. So, because the size of the objects are much larger and they travel with much smaller speed compared to the speed of light. So, simple Newtonian mechanics will do. Now, suppose if we go to extremely large speeds, when the speeds of the objects become comparable to the speed of light, then we need to invoke special relativity. So we need special relativity to study the mechanics of such particles, kinematics of such particles. On the other hand, if we go to subatomic level, so when we go to extremely small size, as we already know, we need quantum mechanics to study the subatomic particles. But what about subatomic particles that are highly energetic? I mean, they move with speeds comparable to the speed of light. In such a scenario, we need to combine both quantum mechanics and special relativity. and as a result, we will have quantum field theory. So this is the framework of particle physics. So in particle physics, we study the interaction of the particles, the scattering of the particles, everything in the language of quantum field theory. So yeah, that is just to mention about this. Now coming back to the particle physics and how they interact. So we already know that all the interactions in the universe can broadly be classified in these four types of the interactions. So these are the four fundamental forces of the nature. And all of us already know about electromagnetism. So it is the electromagnetic force that hold the electrons in an atom, like so that they revolve around the nucleus of the atom. The interaction between the nucleus, positively charged nucleus, and the negatively charged electrons is of electromagnetic type. And we also know about gravitation. Everyone, like all of us, know about gravitation. We experience it on a daily basis. So it's a gravitational force that is responsible for the planetary motion, and also it is the gravity that help us stand and like stay still on this earth. That is holding us to the surface of the earth. If there was no gravity, all of us would have been floating around in the space. Now, there are two other type of interactions. One is weak interaction, which is actually responsible for nuclear beta decay. So we know in beta decay, if there is an unstable nucleus that can emit an electron and a neutron and can become another stable nucleus. So it is the weak interaction that is responsible for such reactions. And there is also strong interaction. So it is the strong interaction that holds the nucleons. By nucleons, I mean the neutrons and protons together in the nucleus of an atom. So we know that the protons are positively charged. So in that sense, we know like charges repel, but the protons are not repelling. Instead, they are stable. The nucleus is stable. They are, stuck together in the nucleus of the atom. And it is the strong interaction that hold these nucleons together in the nucleus of an atom. Now, how these fundamental forces act between particles. So before going to that, like I would like to give an analogy. So suppose like two individuals standing on these boats in this water in a lake. Now, suppose this person is throwing a very big ball to the other person. Okay. So as a result, like there is momentum transfer in this direction, and as a result, the boat in which this person stands, would move in the opposite direction, like recoil. And once this person catch this ball, there is some momentum transfer in this direction, because of which he tend to move in this opposite direction. So because of this transfer of the ball correspond to the transfer of energy and momentum, and as a result, the effect can also be seen on these boats. Now coming to particle physics, you can think of these boats or these persons as the elementary particles, and this ball as the force carrier. So in the most modern view of particle physics, these forces are actually mediated by certain particles, which you can call as the quantum of these corresponding fields. So there are certain particles called as gauge bosons that mediate this interaction between these particles. So like the same way, like it works like this. Suppose there are two incoming particles, and this particle can emit this force particle, which I call as a gauge boson. And as a result, because of this emission, it can recoil, and the other incoming particle can absorb this force particle, and as a result, that will also recoil. So this is how the elementary particles scatter, like in the simplest way, if I'm describing the scattering. Now, again, coming back to the exchange forces and force carriers, as I mentioned, there are four types of interactions. And now corresponding to these four types of forces, there are four types of mediators also. There are corresponding mediators. So first, for the electromagnetic interaction, the quantum of light, it is photon that is mediate electromagnetic interaction. So when two electrons are repelling, it is due to the exchange of photons. Suppose there is an electron and also there is another electron next to it. How do these electrons know that, okay, there is an electron, so I have to repel, I have to move away? So it is the exchange by the exchange of photon. It is this photon that is this that is sending the signal from one electron to the other electron. See, I am here, I have negative charge, so you have to move away from here. And on the other hand, if it is a positron which have a positive charge, the photon would say, okay, there is an electron here, you have positive charge, so let us attract. So that is about the photon. And on the similar way, so there is this weak interaction, as I mentioned earlier. So they are mediated by some particles called as W and Z bosons. And also the strong interactions are mediated by certain bosons called the gluons. So these interactions act among the different particles. So for example, the electromagnetic force act among all the charged particles. So if there is anything that has an electric charge, electromagnetic interaction would act among them. So we have these quarks and leptons. I will describe what quarks and leptons in the next slide. And also these W plus or minus, they are also charged. So they also interact by electromagnetic interaction. Now, like I would also like to mention, now we have unified electromagnetic and weak interaction into one single framework called as the electroweak theory. So what exactly is unification? To give an analogy, initially we used to think of electricity and magnetism as two separate phenomena. And later, by the work of Maxwell and all in the 19th century, now we know that both this electricity and magnetism are different phases of the same phenomena, same theory, like the electromagnetic theory. And now we know that even this electromagnetism and the weak interaction can be unified into one simple framework, which is called the electroweak interactions. And actually, physicists are trying to unify like all these interactions into one single framework. And that was also the dream of Einstein, to have a unified theory for all the fundamental forces. Now, I also would like to mention that like for this gravity, so we assume that like one can assume that it is mediated by something called graviton, but then it is not yet observed. And also the quantum theory of gravity is also, to have a quantum field theory of gravity is also extremely challenging, and so many physicists all around the world are working on this. Now coming to the elementary particles. So these are the basic building blocks of the universe, and this is called the standard model of the particle physics that describes how these elementary particles interact among themselves, how the universe that we see as today is made of these elementary particles, and how they interact among themselves via these force carriers, which I mentioned earlier. So here, like the particle that all of us are like most familiar with is the electron. So this electron is actually a lepton. So these are all these particles are leptons. So there are three families of leptons, and electron. There is a neutrino associated with electron, and there is also something called as muon, and there is a muon type of neutrino, and there is also a tauron which has a tauron type of neutrino associated with it. So these are three families of the leptons, and this muon tauron like have exactly the same properties as that of electron, except that they are much heavier. Muon is much heavier than the electron, and tauron is again much heavier than the muon. Now, as I mentioned earlier, like protons and neutrons are actually made of quarks. So in fact, like it is just the U and D quarks that combine together to form neutrons and protons. And then we have the second and third families of the quarks. So this is the up type and down type quarks, the first family. Second family is the charm and strange quarks, and the third family consists of the top and the bottom type of quarks. So these are the three families, and together these quarks and leptons are called as the matter particles, because all the matter that we see like in the universe are made of these particles. And these are the force mediators, the Z, gamma, W, and G gluons. So these bosons are the force carriers, because these matter particles interact among themselves via the force carriers. And also, I would like to mention that the Earth that we see, the particles with which that we are familiar with, like everything is made of atoms, as we know. The atoms are made of protons, neutrons, and electrons. So it is only this up, down, and the electrons that exist in this Earth, like are the particles which we can relate to. The all other heavier particles, since they are extremely energetic, they would always decay to these lighter particles. because we know whenever a particle that has nature always prefers states of lower energy, because that means lower energy means better stability. So yeah, all the heavier particles would always mu1 and tau1 always tend to decay to electrons and neutrinos. Okay. Now there is also this Higgs boson. This Higgs boson which is known as the God particle. So this holds a special status in the Standard Model because it is through the interaction with the Higgs boson that all the other particles get their mass. So the photon is massless, and the photon doesn't interact with the Higgs boson, and as a result, the photon is massless. And neutrinos are also deemed to be natural, deemed to be massless in Standard Model. Now, how the Higgs boson give mass to all these particles? So one analogy is that, for example, we can consider a room full of physicists, and someone who is very famous, like if Professor Higgs is going through, then all the other physicists, all the other scientists would want to interact Professor Higgs. So because see, all these particles, so these particles we can think of as Higgs field. Particles we can consider as like heat Peter Higgs. So when he is going, everyone want to interact with him. So is strong, and there's a very. On the other hand, if someone like me is going, like I'm not that popular. If few of people know me. So if I am going like that, like the interaction will be weak. So not many people will talk to me. So that is like the electron. So not many particles, not the Higgs field interact with the electron. This is the mass of the electron is field. On the other hand, photon, no one knows the photon. So Higgs field would the photon at all. The photon is constant. Okay, so different particles get depending on how strongly these particles interact with Higgs field. Now, coming to this field discovered at the Large Hadron Collider. So, in this collider, the scientists do is these protons are accelerated to very high energy, very strong energy, and all particles are produced including protons. Really need other particles. But then one can also track like track back and see the signatures of the Higgs boson in the decay. So that is how Higgs boson is observed, and this is the Large Hadron Collider in J. And yeah, the CERN, Higgs boson, the so-called good particle was discovered at the Large Hadron Collider in 2012, and Peter and I'm not understanding. Like, am I visible? I don't know if I'm audible. Okay. So yeah, as I mentioned, uh, neutrinos are everywhere. So they come from particle accelerators, neutrino reactors, and nuclear reactors, sun, from the crust of Earth. So everywhere there are, and also there are these cosmic Big Bang neutrinos, like from the early universe, and like neutrinos are also coming from the Earth's atmosphere, like which is produced from the cosmic rays. So like that. Now, what is so special about neutrinos? Like we'll say, and like first of all, it's very these neutrinos because we need extremely huge detectors. As I mentioned earlier, these neutrinos detect very few matter, and like in 1 second, for example, there are like hundreds, billions of neutrinos all around us. Uh, like hundreds billions of neutrinos like passing through our body, like second. But only one of those neutrinos would interact with our body, say in 100 years. So that difficult it is to detect this neutrinos, and hence we need extremely huge detectors to detect these neutrinos. So this is the typical size of a neutrino detector. So this is the size of a man, like whereas this is the size of a neutrino detector. So and a neutrino detector of this size can have approximately 300 interactions per day. So yeah. Now coming to the solar neutrinos, the neutrinos coming from the sun. As I mentioned earlier, sun like gets its energy from this nuclear fusion. This hydrogen nuclear fuse together to form helium, and in this process, lot of neutrinos are released along with this with energy, and these neutrinos can reach Earth and can be detected in the detectors on the surface of the Earth. So actually, these neutrino detectors are like most of these detectors are underground because to screen from other background noises. Okay, so this is like the Sudbury Neutrino Observatory in Canada, and this can detect all three types of neutrinos. And this detector has 1,000 tons of heavy water. This water with deuterium in it. So when these neutrinos fall on this detector, pass through the heavy water, it can interact with the deuterium, and then neutrons are produced, and one can track the neutrons and then detect neutrinos like that by tracking the neutrons that are produced. So there are like neutrinos also coming from the atmosphere, as I mentioned earlier. So there are like cosmic rays coming from all sort of sources, and there are like this cosmic rays consists of all sort of particles, including pions, and these pions can decay to produce neutrinos. And so we have also detected the atmospheric neutrinos. So this is the super Kamiokande detector in Japan is the largest current neutrino detector, and this has like 50,000 liters of water. So why do we use water to detect neutrinos? So because like when these neutrinos interact with the matter on matter in water, so it can produce the charged particles, electrons and muons. And when these charged particles move through a dielectric medium, something called Cherenkov radiation can be produced, and we can track this radiation, and that way we can track the neutrinos. So these superchemical detector can detect say 5 to 10 neutrinos per day, even though 10 to the power 25 neutrinos are passing through it every day. So as I mentioned, neutrinos are very hard to detect. Okay, now these neutrinos are puzzling because so there are like two major puzzles. Like one was the solar neutrino puzzle. So this there is something called the solar model. The solar model predicts how many neutrinos are produced from the sun, like how many neutrinos we should detect on Earth if we are trying to detect the solar neutrinos. But when like in the experiment, like when we tried to detect the solar neutrinos, it was observed that like only the 1/3 of the actual expected neutrinos were detected. So actually, so I have to mention that the neutrinos that are coming from the sun are actually that are emitted in the sun are actually electron type of neutrinos. So, we were looking for the electron type of neutrinos, and then what we observed that only 1/3 of the actual expected electron neutrinos were observed. So, and like, why was it happening? Like, people even thought, okay, there might be something wrong with the standard solar model, or there might be something wrong with the neutrinos. Now, again, like, there was also this atmospheric neutrino puzzle. Again, there was a deficit in the neutrino flux. So, atmosphere, like, from atmosphere, like, muon neutrinos are produced. And these, we observed only half of the expected muon neutrinos. So what was happening? So the solution turns out that, in fact, one type of neutrino, suppose there is a muon neutrino produced in the source, that can actually change into another type of neutrino, an electron type of neutrino, or a tauron type of neutrino while traveling to the detector. So when the solar neutrinos travel from the sun to the earth, it has to travel like thousands and thousands of kilometers. And while traveling, these electron neutrinos were actually getting converted into muon and tauron type of neutrinos. On the other hand, like in Earth, we were actually looking only for the electron type of neutrinos. Later, like when scientists came up with the detectors that can detect all the type of neutrinos, it was found that, okay, the neutrinos are not going anywhere, like they are coming, just that they were getting converted from one flavor to another flavor. And this phenomena, this process of conversion of neutrinos from one flavor to another flavor is known as neutrino oscillation. Then it is called as oscillation because the probability for the neutrinos to convert, that function is oscillatory. It is a sine square function. That is why we call it neutrino oscillation. Now, why is it important? Now, it turns out that such a conversion of neutrinos from one type to another is possible only if neutrinos have mass. So, as I mentioned earlier, the standard model of the particle physics that describes the matter and interaction says that neutrinos are massless. But then now, the neutrino oscillation have shown that neutrinos have mass. So we need to have some new theory. We need to go beyond the standard model. We need to go beyond what we already know. So how these neutrinos get mass is still an unresolved problem, and scientists are working on building models that can explain how neutrinos get mass. And then experimentalists are also looking for signatures uh, to see, like, if there are some new particles that is giving mass to the neutrinos. So this is one of the most fundamental issue in particle physics today. And yeah, like the neutrino oscillation, discovery of neutrino oscillation was awarded the 2015 Nobel Prize. So Takaaki Kajita and like Arthur McDonald, they were given the Nobel Prize in physics in 2015 for the discovery of neutrino oscillation. So yeah, this is like, as I mentioned, now I will discuss some open questions in particle physics today. So as I already mentioned, how neutrinos get mass, we still have not understood. There are several proposed mechanisms, but then we still do not know which is the actual mechanism, because for something to be called as theory, it has to be verified at the experiment. So experimentalists also are also looking for to verify these models at the experiments. Now, another issue to which we don't have an answer is the issue of dark matter. What is the nature of dark matter? So, in my talk, I never mentioned about dark matter till now. So, I will briefly discuss, like, how do we know that there is dark matter? So, the dark matter. Uh, so we know that there is dark matter only from its gravitational effects. From the there are certain astrophysical indications that show that there is some unknown kind of matter in the universe, which is named as the dark matter. But then we don't know what it is or how they interact. Like nothing. We know nothing about the dark matter. So one of the indications for dark matter is from the rotation spectrum of the stars in a galaxy. So this is a galaxy. So like the planets revolve around the sun in our solar system, the stars also revolve around the center of the galaxy. And the speed with which these stars revolve around the center of the galaxy depends upon the matter the mass of the matter inside the galaxy. And how do we know how much mass is there, how much matter like and energy is there? That is from the light emitted, from the luminous matter, we know. So simple, like by using simple Newtonian mechanics, we can calculate the speed of the galaxy stars as we move away from the center of the. This is the speed of different stars at different speeds from the center of the galaxy. So if we take only the luminous matter, this is how the speed of the stars vary. But then what actually was observed is that the speed of the stars follows follow a behavior like this. So like this is a problem because it means that there is some more matter, some more mass within these galaxies which we don't know, which is not luminous, because this is by in comparing it with the luminous matter. But then this is some other kind of matter. We know that there is some mass, but then we don't know what it is because it is non-luminous. So this is one of the indication for the existence of dark matter, and the existence of dark matter has been shown in various other astrophysical experiments as well. So yeah, this is one of the fundamental issues, and some other issues. Now, why there is more matter in the universe than antimatter? So it is known that the universe, like the universe that we know, like the Earth and the solar system, everything is made of matter. And that is the reason why we exist, because had there been equal amount of matter and antimatter in the early universe, this matter and antimatter for an electron and positron would annihilate, right? And there would be just light. So same way, like matter and antimatter would annihilate and none of us would have existed. So at some stage, there was some mechanism that produced more matter that led to the dominance of matter in the universe. How did it happen? We don't know. So this is also something that the scientists are working on. And now, like earlier, I mentioned 4 types of fundamental forces. Now, are these the only 4 fundamental forces? Like, are there more? So we don't know. Like, people are looking for that in the experiments. Now, again, grand unification. As I said, like the Einstein's dream was to have one unified theory for everything. So can we unify? Like now we already know, as I mentioned, the electromagnetism and weak interaction are unified to form electro-weak interaction. Now we also would like to unify strong interaction with that, and in future maybe we would also like to unify gravity with that. But then for that we also need a quantum theory of gravity. So how does it work? We don't know. So these are some of very fundamental questions that scientists are working on. And in this pursuit, everyone has to play a role. Everyone plays a role. Just some theorists sitting in their office and doing some calculations will not do, because science always has to, science always progress with experiments. So this has to be probed in experiments also. So we need experimentalists and we need engineers to build huge detectors, huge experiments to detect these particles, to detect new physics. And then we need people with expert in computations, like computation analysis. We need, because a huge amount of data are coming from the experiments. So to analyze these data, we need people with expertise in this large data analysis. And then even before these experiments are built, we need to do the simulation studies, because a lot of money is also involved. So we need to do simulation analysis to study the physics prospects of these experiments. So like everyone can play a role in this pursuit of truth, in this pursuit to understand the universe better. And coming to a broader picture, like the basic science cannot proceed on its own. The development in science and the development in technology are very closely related. One cannot develop without the other. So the fundamental, like history has shown that the development in fundamental science has always led to the development in technology, and the development in technology would always help us to uh, to improve our understanding of basic science. So some simple examples are that the particle accelerators and the detectors, like they are used now in medical research. So, and they're even used in cancer treatment. and these advanced computing technologies, like even this artificial intelligence, machine learning, these most modern techniques are also used in the data analysis for this particle physics experiments. And then, like, yeah, in several ways, it has actually, the research on particle physics has actually improved our quality of life. And yeah, like, having said this, I'd like to stop my talk here. So yeah, thank you. So, are there any questions, comments?
Thank you, sir.
Hi.
It was a knowledge fact session with interesting facts. Mm. And by this, our program has come to an end. Now, I take this opportunity to thank our college administration, especially our principal, Dr. Joy K.N, our vice principal, Reverend Dr. Martin Kolambrath, and IQAC coordinator, Dr. Father Anil George K, for giving an opportunity for conducting this event. I also extend my sincere gratitude to the resource person, Dr. Vishnudath K.N, for spending his precious time from his busy schedule. I also thank my friends, colleagues, and all others who wholeheartedly supported to make this event possible. Once again, I thank each and everyone. Thank you so much.